Hey everyone, how you guys doing? I am going to talk today about collision theory. Hooray! Usually I can get through collision theory and reaction energy profiles in one go, but because we're distance and everything, I'm going to take it a little bit slower and um, split them up into two separate lectures. So let's talk about this thing. We've been talking about kinetics. We've been talking about these elementary reactions, these little sub reactions that happen, little steps that are part of a much larger reaction. Um, so we talked about molecularity, like if in this case, since this is a third order reaction, we know that there are going to be a three body collision. In other words, three molecules are going to be slamming into each other. This is pretty rare, but it can happen. So let's kind of think about that for a little bit. That molecules, in order to react, do have to slam into each other. They do have to collide. So this makes sense. If two molecules aren't touching, they can't do anything together. They can't interact. You have to have them hit each other. Okay? And not only that, but just because two molecules hit doesn't mean that they're going to react. This would actually be really bad for us if anytime two molecules hit, they would immediately react. Think about it. We have a bunch of oxygen around O2, and anytime an oxygen hits another oxygen, if it always made ozone, O3, we would all be in trouble. We would all suffocate and die very, very quickly. So, um, there has to be some things going on, not just that they collide, but they have to collide and stuff. So, this dude is the guy that figured out a lot of this. His name was Arrhenius. You might remember him as the acid and base guy. Arrhenius acids, Arrhenius bases. He kind of put forth that molecules have to hit with enough force in order to actually do anything. So they have to have enough energy going. And he called this the activation energy. I'm not going to go into this a little bit more detail in a different lecture, but just so you know that there's always going to be kind of a starting energy, an ending energy, and there's always going to have to be this hill you have to go over in order for the reaction to go forward. Think about this as like a match, right? You have a match. You need to put a little bit of energy into a match in order for that reaction, that flame, to actually appear. So it just has a little bit of an activation energy for it to go. Some reactions have a very large activation energy, in which case we're going to need to put in a bunch of energy in order to get that reaction going. So that is that. So that's one thing that you have to think about, is that these particles have to slam into each other with enough force. Okay, and we'll get into kind of a lot more stuff like that later. Temperature, kinetic energy is a great way of doing this. One way to think about it, remember, if we are increasing temperature, what we're doing is increasing the kinetic energy of a portion of those particles. So if we have this activation energy here and we increase the temperature, we're going to have more particles being able to get over that activation energy hump, to jump over that hill. So if we increase temperature, we're not messing around with the activation energy. What we're doing is we're making sure that the particles have enough energy to get over the hill. So increasing temperature does not change the activation energy. It just increases the energy of the particles. We're not lowering the activation energy at all. Okay, so activation energy is one thing you have to think about, but we also have to think about orientation. So this is something called steric factor. Steric is just kind of means kind of positional. Okay, So a steric factor, it's a number between 0 and 1. You don't have to worry about it. You just need to know about the concept of steric factor. Think about this. If we have two NOBR, and they collide to make 2 NO and Br2. All right. So think about it this way. If it hits like this, then you can imagine that the bromines can actually form bond and move on. If it hits like this, the bromines can still hit a bond and move on. But if it hits like this, where the oxygens hit, the bromines are so far apart that no bond can actually form in this. So not only do they have to hit, but they have to hit the right way. Kind of think of it like, imagine you have like a tennis ball, and one of those, you remember as a kid you had like those paddles with Velcro on it, you know? If you threw a tennis ball up in the air and then you threw the Velcro pad at the tennis ball, the ball has to hit the Velcro in order for it to stick, right? If it hits the backside of the little paddle, then it doesn't do anything. It just bounces off. So it has to hit in the right manner. It has to hit in the right orientation. Okay. So one thing that you can do is increase the frequency of these collisions. And the way you can do that is by increasing pressure. So we can think about it, if we increase temperature, what are we doing? We're making the molecules move faster, and that's adding more kinetic energy. So we're being able to jump over that activation energy hump. Here, with pressure, we're increasing the frequency of these collisions. We're kind of making it to where we're adding more chances that it hits in the right orientation. So there's that. Now we can kind of go through and add all of these boys together. We can go through and think about the activation energy and the temperature and the gas constant and the steric and the number of collisions and all of this, and then put it all together, and we get this Arrhenius equation. Now, you won't have to know this Arrhenius equation at all. The only thing I would like you to know, and you can go through and like calculate things. You won't have to worry about this so much. But what I want you to know is the following. This is a good way of finding the activation energy. You don't have to know all of this. In fact, here, I can even show you. Calculations involving Arrhenius equation will not be assessed on the AP exam. Hooray! What I want you to know, though, is the following. How do things affect K? And this is K as in the rate constant, lowercase k. How do these things affect K? So if I increase temperature, what is that going to do? If I increase temperature, how is that going to affect K? If I increase temperature, K is going to also go up. We're going to increase the rate of the reaction. If I increase the frequency of hitting things, if it's easier to hit, if you increase the number of particles, if you increase the number of collisions, all of those things will also increase K, which means it's going to increase the rate. All right. What happens if I decrease the activation energy through some means that we haven't got to yet? We'll get to that in a little bit. But if we decrease activation energy, that's also going to increase K, increase the rate. So just go through and remember, if I give you two molecules, right? Let's say I have O2 versus that NOBR. Which one of these guys, under the same conditions, if everything else is kept the same, which one of these two is going to have a faster reaction? This guy is going to have the faster reaction because it's easier to hit at the right side. There's no steric hindrance here. This one, you have to actually hit the bromine on the right side in order for it to actually have a reaction. So there you have an increase of steric hindrance. It's harder to hit, so it's going to be slower to go. All right, guys, that's it for this one. This is going to be on Edpuzzle. Make sure to go through and actually hit submit at the end. If you don't, then you don't get a grade. So yeah, make sure you can go through and actually hit submit. All right, guys. I will see you guys tomorrow. We'll have a Zoom meeting at our usual time. Bye.